For these examples, we're going to be asked to find the global extrema, if they exist, of a given function on a given interval. Now, we're not going to have the guarantee that they exist because the function may not be continuous or the interval may not be closed, but we need to be able to assess what's happening even at the places that could be problematic places like open endpoints or places of discontinuity, and still assessing those individual places along with the other places like critical points in the interval and the closed endpoints. We can still figure out when we do have a max what it would be if it is, and likewise for a min. And so for this particular example, we have a polynomial function. Polynomials are continuous everywhere. So that's one thing to notice. And so we're not going to have any particular places that could be problems based on continuity. But notice that we do have a missing endpoint. So we have an open interval, we'll say, open on this side. Closed on the other, but we've got open on this side. So what we need then is we don't have any places of discontinuity, but we do still need to figure out what we have for critical points. So let's look for critical points. For critical points, we need to take the derivative, and so we've got f prime of x is going to be negative 2x minus 2, and that derivative is defined everywhere. So f prime undefined is nowhere. But we can figure out where it's 0. F prime equal to 0. We set that factor equal to 0 and solve. So we could add over the 2. So we've got negative 2x equals 2. Divide both sides by negative 2, and that would give us x equals negative 1. That is in the interval. It's always important when you get critical points to assess whether or not it's in the interval, because if it's not in the interval, you just don't worry about it at all. And so we've got two sorts of things to deal with. We have plug-in values and we have limit values. So our plug-in values are the critical points that are in our interval. So we've got the negative 1 that is in the interval. But it's also the endpoints that are included, so the closed endpoints. And so we've got 0 as a closed endpoint, and so we need to plug that into our function also. And so those are our two places where we're plugging in. Let's go ahead and do that. So we've got negative 1 in parentheses squared minus 2 times negative 1 plus 4. So that first term there is a negative 1 squared. So the negative 1 squared part is back to positive 1, but we've got the negative 1 out front. So, or the negative out front. So we've got negative 1 and then plus the 2 because of the two negative signs. So we're up to positive 1 and then plus 4, so we get up to 5. When we plug in 0, we have the negative 0 squared minus 2 times 0 plus 4, so we've got a 4. So those are our two plug-in values. We've got the critical point that was in the interval, and we've got the end point that was included. And then we've got limit values. Okay, so the limit values would come from any place that any discontinuities. We would need to look at both sides of a discontinuity to see what's happening, but we didn't have any discontinuities, so that's not something we had to deal with for this example. However, we also, for limits, need to look at the endpoints that are not included. And so in this case, we're looking at the limit as x goes to negative 3, and it's coming in from the right because our interval is to the right of negative 3. The left endpoint, we would be looking at what's happening coming in from the right side because the right side is the part that's inside the interval. So the limit as x goes to negative 3 from the right side of the original function. But see, this original function is a polynomial, and taking the limit of any polynomial amounts to just plugging that value in. And so what we get then is the negative 3 squared minus 2 times negative 3 plus 4 And then if you do that computation, you should get 1 when it's all said and done. So we have 3 numbers to look at, and we see 5 is the biggest, and we see that 1 is the smallest. Okay, and so we can say that we have a global max because the 5 that's the biggest came from a plug-in value. But we do not have a global min because the value that was the smallest came from a limit value. And so what that's saying is, as we if we had this graphed over that half open interval, what we would have to do is include an open circle there at -3, and that would be the lowest point at -3, 1, and so that potential min is not there because the endpoint is not included. And so our final conclusion is a global max. Actually, let me scoot this over here. Global max of 5 at x equals -1, and no global min. And so that gets us our final conclusion for this particular example. Now we have another example here that has the same directions. This time the function has a discontinuity and let's figure out if that's in the interval or not. But we do have a closed interval. And so let's look at discontinuity first. So the discontinuity is going to be where the bottom is equal to 0 of my original function. So we're talking 4x minus 1 squared equal to 0. Well, that squared, we could just square root both sides, and we're looking at 4x minus 1 equal to 0. Add over the 1, divide by 4, we've got x equals a fourth, and that is in the interval. And so that is a discontinuity place that we've got to be careful about. So let's look now to see what critical points we have. We get critical points by taking the derivative and setting it equal to 0 or figuring out where it's undefined. So we'll go ahead and take the derivative. I would rewrite the original function, since it's just a constant on the top, I would rewrite the original function as 4x minus 1 to the -2 so that my derivative is quicker. Using just a chain, just a chain rule. So bring down the power -2. We've got the 4x minus 1 now to the -3 because we dropped the power by 1. We take out the derivative of the inside, which is 4. And so then when we write this up nicely, we have the -2 times the 4, which is -8. And then we could push down that factor of 4x minus 1 to the third power on the bottom. So there's our derivative. We can figure out where it's equal to 0 and undefined to get critical points. So the derivative is 0 where the top is 0, but the top is never 0. And so we don't get anything from there. The place where the derivative is undefined is going to end up being the discontinuity that we started with, because it just amounts to setting the bottom equal to 0. And it's going to play out exactly like it did algebraically for the discontinuity. So that would give us x equals 1/4, but it's not in the domain. So it's not a critical point. And so for this particular example, we have no critical points that are in the interval. We have one discontinuity, and we have both endpoints that are included. And so here's what we've got. We've got plug-in values. The plug-in values would be the critical points, but there aren't any. And they would be the endpoints that are included, and both endpoints are included for the interval. So we want to plug in both 0 and we want to plug in 1. And so we plug that into the original function. So we've got 4 times 0 minus 1, and we're going to square it on the bottom. So that would be a -1 squared on the bottom. So we're looking at a 1 on the bottom. So we're talking 1/1, which is 1. When we plug in the 1, we've got the 4 times 1 minus 1, and we're going to square it. So 4 times 1 would be 4, minus 1 would be 3. Squaring it would be 9 on the bottom, so we're looking at 1/9. And so those are the only two plug-in values, but we need to compare it to what's happening at the discontinuity, because right now our candidate for the biggest is the biggest value being 1 and the smallest value being 1/9, but we need to see if the discontinuity is going to throw that at all. And so let's look at, we'll say limits. So in general, for limits, we have to look at both sides of what's happening at any discontinuity, and we need to look at the endpoints that are not included. We don't have any endpoints not included, so it's simply the one-sided limits at the discontinuity. So we've got the limit as x approaches 1/4 from the left for the function, and the limit as x approaches 1/4 from the right of the function. And so what's happening here is we plug in, we know that when we plug in 1/4 for the bottom, we know that's going to make the bottom 0. So the key is the 0 eating up a positive sign, or is it eating up a negative sign on the bottom? And so here, what we would have is a 4 times something slightly less than 1/4. And then we're subtracting 1 from it, but we're squaring it. And so the squaring it part is actually what's going to keep it positive, a 0 with a positive sign for both of these on the bottom. So we've got 1/0 plus, because no matter what we plug into the bottom, it's going to be positive or 0. And so whether we're slightly to the left or slightly to the right of 1/4, no matter what's inside of the parentheses, slightly bigger than or slightly less than 0, we square it, and so it's going to be slightly bigger than 0 if we're looking at just off of 0. And so the 1/0 plus is non-indeterminate positive infinity for each one. And so what we see here is that the biggest is positive infinity. And that happens really on both sides. Okay? And so this candidate here that we had as the biggest so far, being 1, is thrown away, because we've got either side of this asymptote at 1/4 going up to positive infinity. So that's definitely overtaking for the interval. But the smallest is going to be the 1/9. And so what we end up having as our conclusion for this problem is global min of 1/9 at x equals 1 and no global max. And so to be able to do these sort of generalization problems, what we really need to keep track of is we have plug-in values and we have limit values. The plug-in values are critical points that are in the interval, and they're endpoints that are included in the given interval that we have. And so anytime our biggest or smallest comes from a plug-in value, that's going to be the global max or min. But then the limit values are both sides of any discontinuity that we have, and the one-sided limit for the endpoints that are missing, so the open endpoints there. So those are places that we have to see what's happening at the problem spots, and if any of those happen to be the biggest or the smallest, then our conclusion is that we don't have the global max or the global min, respectively. And so just keeping track of where the numbers, when you're plugging those into the function, where do they come from, that helps you be able to make your final assessment.